So hi everyone, let's start. So today we will finish the example of the Hermitian function field we began last time. So let me recall. Let P be some prime number and Q P squared. Then we introduce the function field E FQX with a new variable Y such that this relation holds. And there was a theorem that this is indeed a function field. The constant field is FQ. And it will be a consequence of something that Gil will prove later, but let's take it as given. And what we wanted to show is to explore what are the rational places of this function field. Rational places, just prime divisors of degree 1. So we'll get, so maybe one more before that, let me just recall. So if we consider this extension of FQ over FP, FP squared over FP, then we saw the trace and the norm, two important maps. What was the trace? Do you remember? Trace of alpha was alpha to the p plus alpha, and the norm was alpha to the plus 1. So if we think of the Hermitian curve, like curve all the xy in fq squared, such that yp plus 1 is equal to xp plus 1, then what is this equation? It's just the trace y equals the norm x. So, and we will see today why is the convenient work with this equation. So, okay, so the motivation is that for a good GOPA codes, we want function field with as many as possible rational places. So this will be like the rational places are the evaluation points. Like in Reed-Solomon codes, the message is a polynomial and we evaluate it at some points in the field. And now in the GOPA code, instead of polynomial, we take function from a Riemann-Roch space and we evaluate at some prime divisor of degree 1, at some rational place. So the length of the code word is just the number of the rational places. Okay. So what is a place? So what is a place? So we have E.
So you want them to be large or to be small?
So I want a function field with the more rational places, the better.
It would be proportional to how many errors you can correct.
Yeah, and we will see. Okay, we will discuss it. It will be, yeah. So for now, just let's try to find how many such places are for the Hermitian. Okay. So if we in a picture, we have the rational function field. We have the Hermitian function field. Now, after today, you know that this is just a particular case of function field extension, but we won't need it today. And what is a place of degree 1? A rational place, a prime divisor or of degree 1 is just a place from E to where? Right, so if it is of degree 1, then what's the degree of the place? So the residue field, the OP mod MP, is some finite extension of FQ, and the degree of this extension is just the degree of phi. So a place of degree 1 is just the residue field is an extension of degree 1 of FQ, or just FQ. And it's good. So the evaluation, the code words will be the values of the okay. Code words will be in FQ to the n. And the infinity of code. And it's a place of a function field, so it should be non-trivial on E. Some function in E should be mapped to infinity, and trivial on the Q. And without loss of generality, we always assume that it's the identity of FQ. Every constant is mapped to itself. And
Because they're all equivalent.
without loss of generality, we can identify exactly. We discussed this. So how can we find such phi? What is the natural thing to consider?
Yeah, most of the question who works to one.
Okay, so let's consider the restriction to FQX. FQX. Okay, so the first question is, what is the residue field here? So again, it should be if the restriction is a place of the rational function field, then it should be some finite extension of the constant field FQ. So it should be some finite extension of FQ. But we already saw last time that this residue field can be embedded in this residue field. So there is only one option, it should be FQ as well.
Can it be like FP?
It's a finite extension of FQ, so it's at least F.
So it's an extension of it.
Yeah, and it's actually just by the restriction, if it, yeah. So
It's the other way. Yeah, it's supposed to be smaller than FQ.
No, it's always at least FQ, and if we insist that the above is 2FQ, then there's only one option.
I see. So that's to make sure I understand. So phi restricted is always smaller than phi.
Right. So
but
when we go,
it is FQ, then it's FQ.
Yeah, exactly. And if we start with some place below and go up, then the residue field can be larger than this, some extension. But yeah, but okay, so if every value of phi goes to FQ, then the restriction is also to FQ. Yeah, okay. So in other words, the restriction is a place of degree 1 of the rational function field. And okay, and again, there is assuming that is indeed the place of the function field, that it's trivial on FQ and non-trivial on FX, but we will see that it will be the case. So don't worry. And then what are the options? So there are two. So what are the options for if this is indeed the place of degree 1 of the rational function field, then let's talk about the valuation. We know what are the valuation of the rational function field. One is up to equivalence is V infinity, and V of x minus alpha, or the alpha, for every alpha in FQ. This is the valuation, the place that this corresponds to the place that substitute alpha for x. So there are two cases. So let's suppose we have such phi, consider the restriction, assume that it is indeed a valid function, a valid place of the rational, so its valuation is equivalent to this or to this. So if this is the case, in fact, in other words, if the restriction sends x to infinity, then the valuation of x is negative. So the valuation of x is below is equivalent to V infinity. This was the case that we did last time. And we analyzed so last time we handled this case, and the bottom line was there is a single place above. So there is only one place above. such that when we restrict it, we get the place corresponding to the valuation v infinity. And okay.
If we have the reduced place, we know exactly what the original one.
Yeah. So there is one place of E over FQ, such that when we restrict it to FQX, we get the place which is the place that its corresponding valuation is after equivalence, it's been infinity. So the remaining case is to handle the second case. So let's do it. So if X is not mapped to, so this was last time.
Just like to dash it in, like the short bottom was the bottom line was what is the V infinity? The bottom line.
Oh, so V infinity above the valuation V infinity above. If you remember, it was it sends
Y to something, and it was like some constant multiplied by.
So after we normalize so that V will be onto Z above, it was the valuation that sends X to minus P and Y to minus P plus 1. So you can see like last time.
Yeah.
So yeah. And if you know the valuation of X and Y, you can easily find the valuation of arbitrary element of it. It was an exercise when it's in the notes. So now consider the other case that we started with phi such that the restriction, now X is not mapped to infinity, but to some alpha in FQ. In other words, the evaluation of the corresponding place is V alpha. So what is the place above or the valuation above? Okay, so in other words, phi of FQX is just phi alpha. So let's call this phi alpha, just substitute alpha for it. So in this case, what is phi of, what can you say about the phi of y to the p plus y?
Phi.
Okay, so first,
P plus 1.
it's phi of x p plus 1, right? Because this was in E, these two functions are the same. And what is this? Like just phi of x to p plus 1, since it's a place. And if phi of x is just phi the restriction and alpha plus 1. Yeah, so if the restriction sends x to alpha, so also the phi sends x to alpha. Okay, so in particular, this function is in the evaluation ring of this place, right? It is not sent to infinity. Sent to some value, alpha to p plus 1. And in fact, follows that.
Why is that? Why can't we go to infinity?
That's the image. Yp plus y is not to something like q. And in particular, it follows that if, let's call the evaluation above v, that v of y I claim that it must be non-negative. Can you see why? The usual things with evaluation, if it was strictly negative, then what was this thing? It was at least the minimum between PVY and VY. And if it was negative, then PVY is smaller, so it will be PVY, which is negative. But it's not negative because it's not sent to infinity. Okay. So in other words, so y is not mapped to infinity, so P of y belongs to FQ as well. And moreover, if it's a place, then what hence phi y to the p plus phi y is alpha to the p plus 1. Okay? Just properties of place. So, okay, so if x is mapped to alpha, then y must be an element of fq such that 5y to the p plus 5y is alpha to the p plus 1. So the next observation, what are the possibilities for how many possible values are for phi of y? How many roots this equation is so playing? So let's and let me just mention one more thing. In fact, not only lies in FQ, okay, so it's also the norm alpha, right? Alpha is in FQ, and alpha is in FQ, so alpha to the p plus 1 is the norm of alpha, and the norm of alpha is actually in FP. The trace and the norm from FQ are from FQ to FP. So just erase it. But
why alpha is an FP?
because it's the value of the norm function. The norm is from FQ to FP. Yeah. So now claim let beta be some element in FP. Then the equation in t to the q plus t equals beta as t distinct roots in FQ. So in other words, if we take any element in FP then its pre-image of, like this is just place T with the trace of FQ over FP. So take some beta in FP, the pre-image of the trace, all the elements T so that the trace is beta, is of size T. Let's prove it. So this claim is clear. Statement.
So all the method are the same amount of roots and it's
Right. So for example, how many solutions the equation t to the q plus t equals 0 as in FQ, P, and the same for any not only 0 but any element in it.
so there are cosets of the meaning.
Exactly cosets. So so for beta which is 0, we get the equation trace t 0. So trace from FQ to FP is linear. The property of the trace is a linear map. So its kernel kernel the trace, let's call it S0, because beta is 0, is a subset of FQ, a subspace of FQ. The kernel is a subspace of FQ, and it's of size at most. At most Q, for example, right? So polynomial of degree Q over a field has at most Q roots.
I'm sure it's not empty,
Sorry.
then it will be okay.
Oh, sorry, it should be P, maybe not Q. The trace is T of P plus P. And that's why it's at most P. Now it makes sense. Okay. Okay, so for 0, there are at most P, and for beta, which is non-zero, SB is either empty or an affine subspace that Q of the form what form a particular P0 plus S0, where P0 to the P plus P0. So if you can find one solution P0, then the set of solution is P0 plus S0. And if there is no solution, then SB is empty.
You can see better. Yeah.
This is
Everything is zero, so everything is zero.
P0 is some element, some solution, some element, the
Some solution for beta.
For beta, yeah, P0 to the P plus P0 is beta. P beta?
Yeah,
That's the name.
yeah, but
From T beta, okay. And this is S beta.
I think you just show that it's not empty, and as it's a linear.
It's not empty, and we will, yeah.
Isn't enough to show? Okay, so this is.
Yeah, so.
It doesn't empty or it is empty?
Yeah. So if it's empty, it's empty. If which it's not possible, and if there is some P beta which solves it, then the solution is this. The set of solutions is P beta plus S0.
So the first homomorphism.
It's just like a linear algebra.
Image modulo the kernel is.
Yeah, no. Why is it an affine subspace?
Oh, so okay, so
the reason is the size of the group has to be P because
so
it has to divide P. And it's either 1 or the size of the group has to either be 1 or divide P, and P is prime. Or did we not show you? Why does it have to be either empty or of the?
Oh, so claim if so if T beta is one solution, then every element here is also a solution by the linear, right? So just like the solution particular solution to the non-homogeneous equation and the homogeneous equation gives another solution to the non-homogeneous equation. And if you have some solution A beta, which is another solution, then A beta minus T beta belongs to S0. So yeah, you can, yeah, it's a two-line rule. But, so in particular, the set S beta is also of size of most P. Just a translation of the S0. But FQ is the disjoint union of all the F beta. Right, so every element of FQ belongs to exactly one of these S beta. The solution to which beta? Beta, which is the element to the P plus the element. So in particular, the size of FQ, which is P squared, is exactly the sum, the sizes of the S beta. So there are P terms here, and each one of them is at most P, and the sum is P squared, so each S beta should be P. Okay. Yeah, so you can, if you know this good, if not this claims of, you can check it. It's need to do that. But once there is a particular solution P beta for the non-homogeneous equation, then the set of solution is exactly this set, a coset, in fact, of S0, and this argument shows that for every beta, S beta is of size exactly.
How do you know that FQ equals this union? Because the essence
For every element in a
Yeah,
because the essence starts FQ.
Okay. So the bottom line, so we were looking for the value of P of y, and we know that phi of y, the P plus phi of y, is equal to the norm alpha, some element in T. Right? So how many solutions, values are there that phi of y can take? So it follows that there exists beta 1, beta p in a Q, such that the trace of beta y is the norm of alpha. And exactly the P element, exactly P element such that the trace is P of alpha. So if we want that the trace of phi of y will be n of alpha, then yeah, and only these are the so phi of y should be one of those. Okay. In FQ, and it solves this equation. There are P solutions, so it's one of these. And so
So you mean they're not going to exist if they only exist P, right?
yeah, I don't know.
Only exist.
This. Uh, Okay, so now what are the places? So each one is a place of E from E, EI, say from E to FQ infinity, which maps. So FQ is mapped to FQ, X is mapped to alpha, and Y is mapped to beta I, or I from 1 to P. So you can check that this for each I, this indeed defines a valid place of E. Okay, so
Something goes not to E. This is the thing I need to check is that it doesn't. It's not trivial.
it's not trivial, and it's yeah, and maybe that it is the phi of the product is the product of the phi's. But so you can check or believe me that this is a valid place. So how many places in total we get? So let's say the number of n of the rational places of the Hermitian function field is one is the place above the infinity valuation, and exactly for each alpha in FQ, there are for each alpha in FQ, Q options to choose alpha in FQ, and for each choice of alpha, there are P choices of beta. So in total, we get P, Q is P squared, so it's P. In the end of the course, we will see as a Weil bound, which gives a bound on the number n, and if we apply it to the particular function field E, then this is exactly the best we can hope for.
This is the amount of valuations or places or everything on.
Places of degree 1. Yeah, prime divisors of degree 1. Or, yeah. And you can also make sure that all these places are not, they are all not equivalent to each other. Okay, so this was just one example. We did it without using any advanced theory, but in the next week we will develop the theory, and then it will be like easy to get this immediately. Okay, so that's about. So question?
Just to make sure that why did it work? So it worked because when it's FQ and FP, when Q is a P of squared, we'll understand how equations work.
Yeah.
We'll understand generally.
So yeah. So I think that I don't know, but I guess that the motivation to study this function field is that the equation that defines it, the place equals the norm. It's actually this claims was the key. Like for every alpha, there will be P solution. Split every degree 1 place, which is not the place V infinity, will split completely to P distinct places. Yeah.
So the interesting thing is that it only works because it shows specifically this FQ and FP.
Yeah.
So that we know the equation.
Yeah. So we also know the equation and also know how to analyze this, and also But we'll see in general, like for this was specifically for the Hermitian function. For other, we'll have to do something else, and the general theory will work for general, many general. Yeah, and the fact that the fact that the place of infinity had only one place, and for every place V alpha there was a P, beta 1, beta P. Just the two extreme cases. Like one case, there is only one above, and the other extreme is that there are it splits to P above P, which is the degree of the extension of E over SQL. But this will be this is the subject of the next. So don't worry for now. Okay, so let's switch to a new thing. New for not that new. So Adeles and Weil differentials.
Oh.
Okay. Okay, so let's start with some definitions, just so we'll be on the same page. So what is an Adele? An Adele of function field f over k is a mapping alpha from the set of all prime divisors of the function field to F. So simply every prime divisor gives us function. For each point, for each place, we get the function such that what? VP of alpha p or almost all. So in every place we have a function, and we insist that this function will be defined at p almost always, except for some finite number of p's. So we have the space, the set A of all Adeles, the Adel space, set of all the Adeles of f over k, and this is a k vector space. Okay. Actually, we saw that it's an F vector space, but for our purposes, we'll only consider it as a K vector space, would be enough. And we defined also the lambda. Okay, so for a divisor A, we define the lambda space, set of all the Adeles, such that what? Like the Riemann Roch, the VP of alpha p plus VP of A is non-negative for all p. Okay. So this is sometimes we write VP of alpha. So VP of an Adel is just VP of the function that the Adel takes at this place. Okay. And we saw the diagonal embedding how every function, right, the principal Adel, where all the components is the x. And indeed, VP of x is almost always non-negative because every function has a finite number of poles. So this is one way to embed f in it. Just take the Adel that is always x. At every place, it's x. So now, what is a Weil differential? Weil differential of f over k is a k-linear map, omega from where? So a Weil differential is a k-linear map from the set of Adeles to k, such that, right, so Gil just wrote omega belongs to the form AK, the k-linear map from A to K. Same. Right. From K, it's just k-linear maps from A to K, such that what? The kernel contains some space of this form.
So how do you call the lambda phase? Is it an A force or just or that are defined on
yeah, so I think I don't know. Just
there's no name, just
I know that I'm aware of. So it's the lambda space of A, and the Weil differential is just a linear function from A to K such that it vanishes on some space of this form, lambda A plus F for some A B. So lambda is a subset of Adeles, and F, what do we mean that it vanishes on F? When we think of F as embedded in A, by this embedding. So the set omega all Weil differentials is a K vector space. Actually, also here it's even an F vector space, and today you saw that the dimension of the space as an F vector space is what? 1. But we will only need it to consider it as a K vector space, just the set of all Weil differentials. And again, for A and B, the divisor A, we define omega A, all the Weil differentials such that this is 0, that they vanish on lambda A plus A. So, right, so every Weil differential has some A such that this holds. In fact, many, right? Okay, this is a K subspace of omega. And the important thing, what is the dimension? So let's write it here. What is the dimension of the space? Defined to be the dimension over K of omega A, which is the dimension of, so this, just a reminder, so all this, and this is, the reason that it's interesting is this is G minus 1, minus the seg of minus 1. Okay, so all of this was in the plus, and the last one of the theorems that you proved today with Gil is that for each non-zero differential, there exists unique divisor, the canonical divisor, by the canonical divisor of omega, such that omega belongs to capital omega of A if and only if what? What is the relation between A and the canonical divisor? Exactly. So there's a unique divisor B such that omega is in capital omega B if and only if A is less than or equal B, and it is denoted by this. And we saw, for example, that the degree of and the dimension of this divisor. Okay, and the last thing for today. So now, so every non-zero differential is a divisor, its canonical divisor. So if we have such omega, and we have a place P, prime divisor, then we define the valuation. So every prime divisor has a corresponding valuation. And what is the valuation of the differential? Just define to be this P of the divisor, the coefficient of P in the canonical divisor. Okay, so I thought that today we will see the codes, but we'll have to wait for next week. And okay, so let's stop here, and next time we will continue with this, and we'll see how to use differential to get codes from differential.